Okay, let's look at some practice problems. Woohoo! All right, we're given a system like this. So x dot is equal to ax plus bu, y is equal to cx. I don't have a d term. When we compute the controllability and observability Gramian, so here's the controllability Gramian, here's the observability Gramian, we get these matrices. And we can see that these clearly are very different. They are not diagonal or anything like that. Okay, so first thing we do is we take the square root of q, and so here we can go through and show this is the square root of q. So again, it's a positive definite square root. Then we form the product RPR, and we take the singular value decomposition of that product. Okay, and when we do, this is the U matrix, the unitary matrix. This is the singular value decomposition, a singular matrix. So when you do this, you will actually get S squared, taking the square root, positive definite square root, I get this. Okay, so we see that. So notice that this one is quite a bit smaller than that one, but they're not like incredibly small. We now form this product, s to the power 1/2, so I would take the square root of each of these diagonal elements, U transposed R inverse. When I compute this product, this is the transformation matrix I get. When I then transform my system, this is the system, this is what I get. And so before it looked pretty simple. Now it's definitely a lot more complicated looking, but the Gramians p bar and q bar are equal to S, and again S is this matrix. So we went from something that had controllability and observability Gramians given by this to something where now we have controllability and observability Gramians given by that. Much simpler. Alright, so that's the balanced realization. Now, given the system, here is a 2 input, 1 output system with this initial condition. We're asked to do these things. Simulate the system with 0 input and the first try observer. Okay. Then design an observer with both poles at -10 and simulate both the system and the observer in that case. Okay, so the try 1 observer is of this form. So x hat dot is equal to ax hat plus bu, and y hat is equal to c times x hat. We start with 0 initial condition. So it turns out that the system, and both the system and the estimator, actually start with y equals 0. So if I go back here and look, if I take this y times this initial condition, I'll get 0. But you can see that the system, you can go through and show the system is unstable. So the system blows up, but the estimate can't see that. So the output of the system is not able to detect the fact that the system is blowing up. And so as you can see, the estimate gets worse and worse as time goes on. These two should match, but as you can see, they don't match at all. So this first observer doesn't work as an observer, as an estimator of the states, because the system itself is unstable. So that's not a good situation. Putting the eigenvalues now at both at 10 -10. This should be a plus. We get this expression for L with a plus. So this is the characteristic polynomial evaluated at A. Here's the observability matrix inverse times this, And when we go through that calculation, we get this expression. This is actually the correct expression. This is not the correct expression. And A minus LC is given by this quantity. And so our observer becomes this now. So instead of having a regular A matrix, we now have A minus LC, B, and L. So notice I have two inputs to the observer: the input U and as an input Y. Again, I still assume zero initial conditions. Now when we simulate these, I'm plotting Y and Y hat, and you can see Y hat is lying directly on top of Y, and so we can see that the estimator is at least keeping track of the fact that the system is blowing up. Now if we were to actually be looking at the difference between Y and Y hat, this is what we would see. We would see, so the error actually goes to 0. And it goes to 0 within 1 second. So this is an observer. So even though the system is blowing up, the estimator is doing its job well and is tracking that. And so the difference between these two, as you can see, 10 to the minus 3 is even at its worst is small. So this is the deviation of the estimate from the original. But even then, it's small, and it goes to 0. So we can see that this second observer, the full order observer, works well. We'll talk more about observers in the next lecture.